Welcome to UC Science Radio, where we conduct interviews with a range of scientists to learn about the big issues facing our world and what science is doing to help. I'm Molly McGidd, a master's student in the School of Biological Sciences. Today, I'm talking with Dr. Sarah Masters. She's an associate professor in structural chemistry, a director of postgraduate studies in her school, and the president of the New Zealand Institute of Chemistry. At UC, she teaches all aspects of chemistry, from the basics of what an atom is to advanced methods for analyzing molecular materials. Just a note on my interview with Sarah, we were having some connectivity issues even after she had her kids turn off Netflix, so there are a few points where the recording may not be as clear. Kia ora, Sarah. Thank you for joining me at UC Science Radio. I'm curious about what your role is at UC and beyond.
Okay, so I'm an associate professor in the School of Physical and Chemical Sciences. And so I do research, I do teaching, and I also do administration. And I'm also the director of postgraduate studies within the school. So I have a lot of responsibility for all of the postgraduate students from initial inquiry through to graduation.
And if you could sum up your research in a few sentences, what do you do?
So I'm a gas phase structural chemist, which is a very long-winded way of saying that we look at what molecules look like in the gas phase and try and understand their chemistry and what we can do with them by understanding their molecular structure.
So you're basically looking at these really tiny particles and you're figuring out what they look like and then saying, what can we do with them potentially?
Yeah, so essentially it's a bit like being a molecular detective, if you like. So molecules are very, very small and we can't see them with our naked eye. And so I have equipment that allows me to look at those molecules and to get data about those molecules, which I can then interpret to get a structure. And then from that structure, we can begin to understand how those molecules behave and why they behave as they do. And then we can begin to figure out what we can do with them.
So when you're working with things that are invisible to the naked eye, how do you teach or how do you make people interested in something that they can't see or visualize that well?
Yeah, so I think it's important to remember that with the molecules, when you have a lot of them, you can see the sample. So if you have some salt, for example, on your kitchen table, you can see that, but you wouldn't necessarily be able to see the individual molecules or the individual ions of sodium chloride that make up the salt. So when you have a bulk sample, you can see it. It's only when you get down to the very, what we call the microscopic level, that you can't see them. So that's an important point to remember, I think. So in terms of how we make people interested about it, well, just think of all the possibilities, think of everything that we could do with the molecules. So all of the technology that we're using to talk today comes about because of molecules and the interactions that they have with each other. So the fact we can see each other on a screen at the moment, that's because of all the molecules in the screen that are reacting and doing things as we're talking to each other, you know, and then we're talking at a time of national lockdown. And so you think of the scientists that are working at the moment to try and develop a vaccine for COVID-19, for this horrendous thing, this pandemic that's going around the planet. And so there's a lot of uses of different types of molecules, but we have to understand what those molecules look like. So it all comes down to what we call a structure-function relationship. And if you know the structure of the molecules, then you can begin to understand how they function.
Right, so someone might look at your research and say, oh, that seems really interesting, but is that going to be applicable to the world? But it seems like this very basic science of just, I mean, not basic in terms of the complexity of the science, because it sounds very complex, but more in terms of just learning about all of these concepts and sort of making a base of what we know is supporting these huge things, technology and vaccine development and things like that, it sounds like you're sort of the building blocks for multiple types of science. Is that true? Like, do you think it can apply sort of widely?
Yeah, absolutely. And so whilst the molecules that I look at aren't necessarily, the molecules that might be used in a vaccine, by understanding how molecules behave, then you can begin to apply that to related types of molecules. So you're absolutely right. It's what we call foundational research, and it underpins all the other research that goes on. And so we're essentially building up a body of knowledge within the literature that other people can then take and use and apply within their research to do all of these amazing groundbreaking things.
So one thing that I encountered through just looking into some of your lectures and work is that last year was the 150th anniversary of the periodic table. And I'm sure many people in their science classrooms had a periodic table hanging on the wall, so they know what it looks like. But I don't think there's a widespread idea of how fundamental and important the periodic table is to chemistry. So could you talk a little bit about that and maybe about what you did for the anniversary and what New Zealand did?
Yeah, absolutely. No, you're quite right that it was the 150th anniversary of Mendeleev's version of the periodic table. So there were actually versions of the periodic table before this, and indeed after this. There are lots of different versions of the periodic table, but Mendeleev is considered the godfather, if you like, of the periodic table. Now, the periodic table, what it does is it groups elements together. So elements are the fundamental building blocks that chemists work with. So you can't break an element down into anything else other than the component subatomic particles that they're made up of. And so the periodic table, it groups all the elements together based on their electron configuration. So where the electrons sit around the nucleus of the atoms. And also in terms of their reactivity and their properties. And so you're absolutely right that the periodic table is something that chemists use on a minute-by-minute basis, to be honest. We're constantly referring to it in terms of if we have, a target molecule that we look at, is there a way that we can then change that target molecule, perhaps replace a metal within it with another related metal from the periodic table that's nearby to the one you were originally using. So that's one use of it. But yeah, we use it all the time to try and again understand what's going on with the reactions that we see, to understand why things react in the way that they do. So in terms of the event that we had last year, there were various competitions that we had. So we ran some competitions for the school children of New Zealand to get involved and to tell us all about their favourite element, for example. And there was also a limerick competition as well, which was really a lot of fun. We had some fantastic limericks coming through. And that was actually part of the New Zealand Institute of Chemistry. I gave a UC Connect lecture. So the University of Canterbury runs a series of lectures for people, for the general public to come and get involved with all the different types of research and all the different events going on at UC. And so I gave one of those all about the history of the periodic table and what the future of the periodic table could be as well.
What do you think the future of the periodic table is?
So that's the big question, isn't it? So just recently, that seventh row of the periodic table was completed. So IUPAC, which is the International Union of Pure and Applied Chemistry, approved element 118. And so I guess the next challenge for scientists is to try and populate the next row. Why not? We're always looking for new elements. Although they are getting more and more unstable because they are so big. But yeah, absolutely, why not? Let's try and get row 8 of the periodic table. And we never have to stop. We must always keep looking, so we must never stop looking for new elements and new ways that we can use them.
So when scientists are looking for these new elements, are they often synthetic, so made in the lab? rather than sort of found out in the world somewhere.
Yeah, absolutely. So we're getting to the stage now with these very heavy elements that because so I think we possibly need to go back to the basics of chemistry for just a moment. So an atom is made up of protons, which are positively charged subparticles, neutrons, which are neutral, and then electrons, which are these very, very tiny particles all whizzing around the nucleus. And when you get up to these very, very big, big elements, so element 118 has 118 protons sitting in its nucleus. So it's massive and huge number of neutrons, and then you've got all of the electrons as well. And so because they are so big and you have all of this stuff crammed into a very tiny space, they get very, very unstable. So you're quite right that these particles are made in labs all around the world. And they have very, very short lifetimes just because they're so very, very unstable.
So what's the most fun or exciting part of your work? Your research or anything else that you do?
Oh, well, a big, big focus of both my research and the administrative side of my job is working with the amazing postgraduate students that we have within the school. So enabling them to do their best work and to succeed, and that's really where I get a lot of pleasure and a lot of satisfaction out of my job. I'm an associate professor now. I'm kind of getting towards the top, as it were, and so it's wonderful to be able to give back to those researchers who are just starting out. And so I really enjoy working with the postgraduate students who work with me in my group, and with all the other wonderful students that we have in the school to enable them to succeed.
Yeah, I think there's this image of the lone scientist working by themselves, which just isn't real in any type of science you're talking about. There's always people working together, always communities and larger connections between different disciplines and things like that. And I think that's a misconception that really needs to be squashed out, because you always have to be working with people. That's how science moves forward.
Yeah, absolutely. So science, it relies a lot on that discussion, as you have said. So the discussion between supervisors and students working with them, between different supervisors with different expertise in different areas. And that's one area, again, at the moment that we're noticing. So with the shutdown and with the restrictions on travel, so a lot of conferences have been cancelled, for example. And so the scientific community is actually moving quite rapidly at the moment to kind of replace that void, if you like. Zoom meetings, for example, going on between collaborators all around the world. A lot of online conferences beginning to spring up. So the Royal Society of Chemistry, for example, recently ran its annual Twitter poster conference, which gets huge audiences. And so there's a lot of adaptation around how scientists communicate with each other going on at this time. It's very rapidly changing. But communication is so important. We have to talk to each other.
So my last question is, in one sentence, can you say why your work is so important and why we should care about it, the people who are listening?
Absolutely. So if we want to understand how molecules function, we have to understand their molecular structure. It is a fundamental requirement. And therefore, my work is really important because I am providing that information that can be used by researchers all around the world who are developing lots of new materials, drugs, etc.
That's great. Well, thank you so much for talking with me, and thanks so much for your time and for your children's time off of Netflix.
All right, well, thank you very much for your time. I appreciate it.
That's it for today. For more information or to ask a question about any of the ideas raised in this show, feel free to send UC Science a message by email, Facebook, or Instagram. Thanks for listening.